So, welcome, good evening, and warm welcome to everyone who is online, and to all those who are hands-on at Coventry to this light aircraft design teach-in. I'm Chris Wright, as Barry has just mentioned, Chair of the Royal Aeronautical Society General Aviation Group. This series of teach-ins has been instigated and planned by Rashid Ali, Associate Professor at Coventry University, and generously supported by Coventry University. Rashid has a great depth in aeronautical teaching and has given talks at the Society on the use of design software. These teach-ins are in conjunction with the Royal Aeronautical Society General Aviation Committee, GA Committee, which, in the person of Barry, who you've just been listening to, is the Deputy Chair of the committee, and he's organised the registration and webinar aspects. So thank you to all these, and again, welcome to all, and thank you for joining us. So looking at the first slide, the design teach-in contributes to a long-held aim of the GA group to aid light aircraft design. The Society group exists to promote the technical advancement across the full spectrum of GA aerial vehicles, especially in the application of new concepts, design and construction, propulsion systems, electric, electronic and material developments. One of its main aims is to promote cutting-edge design and development and manufacture of aircraft in the UK and elsewhere. As Barry has said, have a look at the Society website under General Aviation for more information on our activity. The science and art of aircraft design and many of the finest designs of aircraft are really beautiful in form and function. Just think Spitfire, Shark, sailplanes, many hang and paragliders, and countless others. Really beautiful. And the design of aircraft is a vast, absorbing and very satisfying topic. We couldn't possibly do justice to design of aircraft in just 4 sessions. However, there is considerable help in the form of software, and the aim of this course is to enable the design process and to use this software to evaluate designs. And we will later on recommend good reading matter to support this course. We'll be looking at key features and considering how these features will affect performance and behaviour. So this slide summarises the seminar aims and ties them in with the session programme. Today, the first session, 18th of January, we'll look at the first 2 aims, making key design choices and following on with performance evaluation and stability. As I said, this will be addressed in the first half of the evening. Then after a break, Rashid will take us through an introduction to Explain. The second session, 15th of February, will address Aim 3, creation of new aircraft design. Third session will address Aim 4, use of software tools in understanding stability and control early in the design process. The fourth session will be after a 2-month break to enable delegates to develop their own designs in Explain, and it will be an in-house practice session at Coventry to try their designs on the university simulators. As places are limited, we're hoping that if the requirement is there for further simulator sessions to be arranged, that will be possible. At present, there are facilities available for about 25 to 30 hands-on simulator trials in an evening. Rashid has arranged for supporting staff to be manning the chat room so that questions may be handled and answered where possible. And I'm now going to hand over to Rashid.
Well, thank you very much, Chris. Welcome to all the delegates online, and welcome to all the delegates who are here at Coventry. Thank you very much for signing up to this RAeS teaching. I am extremely honored that I have been given the opportunity to come and talk to you about something that I hold in high passion. Now, aircraft design, as Chris has said, isn't something that can be taught over a few sessions. The very best we can achieve is to outline the basic design principles and how we can make use of some of the software in evaluating those designs. Now at Coventry, obviously I was talking to some delegates earlier, we don't have facilities for making large airplanes. However, we do make anything between 8 to 10 unique UAVs, fixed-wing UAVs, and we test fly them as well. So we have some expertise here. So in terms of the evening, I'm going to talk very, very quickly about the aircraft design process. Now, majority of the work, as you can well imagine, takes place in what we call the conceptual design review stage. Here, we have to address some fundamental issues as regards aircraft design, particularly the top-level aircraft requirements as to what the aircraft's required to do. We, at the same stage, are also interested in defining some of the systems that that solution might encompass. So the top-level system requirements are also set in stone at that stage. Obviously, the most important thing is when you embark upon aircraft design, you are not the first one to have done so. There have been many hundreds who have done aircraft design successfully. So we like to bank on their experience and look at existing flying aircraft in the class that you are trying to design to establish some key design variables for you to then iterate upon. Now, aircraft design is a very iterative process. Now, for example, I always say to all my students, whoever come across and cross my path, is aircraft design is a very complex subject. It has one design variable, and that's weight. And as you'll see in some of the slides later, that practically everything we do is a function of weight. Whether it is takeoff performance, whether it is glide performance, whether it is the Breguet range equation, whether it is turning performance, everything basically gets down to the weight. Even drag is a function of weight as well. So that's very, very important. So to get your design in the correct, let's say, ballpark, you need to make some early design choices. And those design choices are normally done at the conceptual design review stage. We then move on, once we have got a layout and a format in terms of our likely design, we move to what we call the preliminary design review stage, where we start to cross the T's and dot the I's on many aspects, including some key structural aspects. For example, what kind of loads the aircraft likely to experience. We normally proceed with what we term as the VNG diagram, produce that to establish the loads that are likely to occur on the structure. At the same time, we also like to investigate at the preliminary stage what the key handling qualities of the aircraft are likely to be. So we resort to either analytical means at that stage in modeling the aircraft dynamics, or we can use flight simulation. The purpose of these teachings is essentially to encourage aircraft designers to use these tools in pursuance of evaluating their design before they commit themselves to the more expensive area of design, which is the detailed design review. Now here, we will do component level and system level work, and that may involve running very large CFD simulations, large finite element analysis, extremely detailed CAD and CAM design, etc. So here, it's not costing you a lot of money in terms of time. When you move to the preliminary design review, then the amount of time you spend in actually iterating the design amplifies. And when it gets to the detailed design review, then we're looking at, for even a small change, a lot many man hours. I'll put down these equations not to frighten you, but to indicate that no matter what you do, you will find a parameter called weight or mass. Whether it is dynamic stability, whether it is static stability, whether it is the range, whether it is flying performance, whether it is the power loading, everything boils down to a function of weight. So the first and foremost thing we need to do in aircraft design is to do in the conceptual design review stage what we call a competitor analysis. So to do that, what we do is we look at all the aircraft that are currently flying and have flown and start to get the data for those aircraft. For example, in this particular slide, I am showing you two groups of aircraft. One group is tailwheel aircraft, and the other is a nosewheel undercarriage arrangement. And what you'll also notice is the takeoff weight ranges from around 800 to 1200 kilograms, so certainly light. And for the nose wheels, again, a similar weight. So what can we learn from that kind of information? First and foremostly, people have flown this aircraft, so we know what kind of power their power plant needs to produce for a flight to be possible. We also can establish what kind of wing areas are we looking at. So what are wing areas that are likely to make that flight possible? So we start more or less in that area. We also have the length of the fuselage. So really, by getting this data together, we are getting an idea as to how big the aircraft is likely to be given the all-up weight or the maximum takeoff weight. So that kind of analysis is absolutely essential. So what we then look at, we in particular look at two parameters. One is what we call the wing loading, which is the weight per square meter in SI units, or you can use English money as well. And the second parameter is either the power loading or the thrust loading. Now what that allows us to do is, when we look at that, you can see, for example, in this particular case, we're looking at nose-wheel aircraft. It's the thrust loading. You can see from the slide that the wing loading of around 40 to 120 kilograms per meter squared, with a thrust loading of anything greater than 0.3 going up to 0.7. The greater the thrust loading, the more likely to have more excess power, and more excess power means better performance. So if you're only overcoming the drag, then you're unlikely to have adequate performance. So what we're looking at this stage is to have a thrust loading which is going to allow you to overcome the drag and still have enough excess power available to do some performance. So being in the right area to start off with in the design process is the key. Now, analytically, the wing loading and power loading or thrust loading are analytically traceable or tractable or definable. So what we can do is we can start with the basics, and we can look at the constant velocity turn. We can look at the stall condition. We can look at the cruise condition. We can look at the takeoff condition. And at each of those conditions, analytically, we can define the thrust loading as a function of the wing loading. So you'll see in these equations that the thrust loading which is thrust divided by the weight, is a function of the wing loading and other key design variables. The reason why we need, at this stage of the design process, to look at these constraints is to ensure that we have adequate power available to perform the mission. Now, for example, you might find that the thrust loading required for cruise is too high, whereas if you've chosen a low enough value, you might not have the ability to cruise at the desired speed. So eventually, using these relationships, which we call the constraint relationships, we plot and obtain what we call the constraints diagram. So on this diagram, you will see various aspects plotted. So you will have, for example, going back to the equations before, you have the thrust loading as a function of the wing loading for various conditions, the takeoff, the climb, the cruise, the turning performance, or the stall condition. So what you then have is multiple graphs or multiple sets of results based on changing or varying the wing loading and obtaining the appropriate thrust loading. Then an area of the thrust loading which is the highest is basically what will be needed to satisfy those constraints. So for example, all the areas shown above the dotted line and the solid line, above the dotted line and to the left of the solid line, would be our prospective design area or combinations of thrust loading and wing loading. So for example, when you look at the vertical solid line, anything to the left of it is a possible design space. So choosing a wing loading, if you go further to the left, all that means is if the wing loading becomes lower, your thrust loading becomes higher. Okay, so you have to then balance out those two parameters from a design point of view, and this is done in the preliminary design stage. In terms of the other parameters, we've talked about the wing loading and we've talked about the thrust loading. For us to create our own design in software tools such as X-Plane, we would need to tie down the geometry fairly accurately. Now, to do that, we would need a choice of aspect ratio. Now, aspect ratio, as you know, can define your drag, your induced drag. So the greater the aspect ratio, the lower the induced drag. So the choice of aspect ratio then is important. Span is another variable that we use, and that's important as well. Why? Because if you have too much span, then it gives us the structural nightmares. The greater the span, the greater the material out towards the tip of the wing, and greater the root bending moment as the aircraft is put through its paces. So the span is quite an important one as well. So at this stage, we need to formulate in our heads as to what the likely layout needs to be. How many wings we're going to use. We can have biplanes. Currently, my students are working on a vertically taking off biplane. So it's a eVTOL biplane. So we consider lots of interesting combinations. So again, how many wings you have, whether it is going to be a high wing aircraft, mid wing aircraft, low wing aircraft, that again has serious design implications. For example, low wing aircraft are joy to land, or not as the case may be, especially if they come into ground effect, or the high wing aircraft do a positive landing depending on how you flare them. So all of those things may have implications from either piloting point of view or from an engineering point of view. For example, if you have a mid-wing aircraft and you need to get the spar connected from one end of the wing to the other, it goes to the center of the fuselage. So where do you sit? So those are practical considerations that you often have to consider. In terms of then drag reduction and compressibility effects, if you were to go quite fast, then we are looking at many other design features of the wing, such as the taper ratio, the sweepback angle, etc. So they're also quite important from a design point of view. Everyone will tell you that if you have a good dihedral on the wing, then they are self-leveling in row. So a dihedral allows the aircraft to stabilize in row. So a choice of dihedral at this stage is interesting, but then it poses mechanical issues. How do you create an accurate dihedral whilst maintaining structural strength in the wings where they're anchored in the fuselage? Incidence is another interesting one. So the reason why I'm talking about these variables is because most of those variables define the geometry of the aircraft, which is then what we then need in X-plane to design our aircraft. Okay, so these things are important from that point of view. Again, have we got any high-lift devices? Now, by high-lift devices, we mean flaps, we need trailing edge extensions, we mean leading edge extensions, we need slats, slots, fences, anything that changes the inherent nature of the aerodynamics of the wing. So again, even at the preliminary design stage or even conceptual design stage, we need to make a justification for whether or not we would need any high-lift device. Now, undercarriage design is an art in its own right. If you get it wrong, then it's not very interesting. So we need to consider whether it needs to be a tail dragger or it needs to be a tricycle nose wheel undercarriage. Each has an advantage. Whilst you have a tail dragger, the pilot visibility out of the cockpit is not that great. So whilst we're taxiing on the tarmac, we do a weave to ensure that we're not bumping into things. But because the aircraft's already got incidents, they are interesting aircraft to take off. So those are the choices. But then comes a bit of the black magic area. The black magic area is what I call the empennage design. There are lots and lots of different combinations of how you can design the empennage, from V-tails to T-tails to cruciform tails, etc., etc. There's a whole variety of different empennage configurations that you can have. The principal function of the empennage is to provide the aircraft with the ability of two rotations. One rotation is in yaw and the other rotation in pitch. Now, without those two rotations, the aircraft is unflyable. So the empennage design is rather crucial. If you don't have enough tail volume, if you don't have enough tail area, then it is unlikely to produce the correct moment to counter the moment produced by the wing. Likewise, if you position your tail at an incorrect length, so that's the tail arm that we talk about, the distance between the center of gravity of the aircraft to the center of pressure of the tail. If you get that distance wrong, your static stability is all over the place. So therefore, those are also choices that you need to make. So what we then do is we may make use of some empirical relationships that people have established, especially at the conceptual design review stage, where we will say that the tail area needs to be roughly between 25 to 30% of the wing area, and that does the job reasonably well. Similarly, we have ratios for the fairing, and we have ratios for the control surfaces. Now, for simulation point of view, those empirical numbers are good enough. But then, as you will see, that if the aircraft lacks the performance using a software tool such as Explain will allow you to very easily, quickly change some of those areas and rerun the simulation, seeing the effect of that parametric change. A typical aircraft design cycle, I used to do a lot of work on numerical optimization on aircraft for Shorts Brothers in Belfast in the late 80s. And a typical optimized aircraft design would be anything between 4,000 to 8,000 iterations. So it does take a long time to hone onto optimal values that will give you the performance that you're after. Ultimately,
Rashid, this is Chris Wright, just breaking in briefly. First thing, do you have someone assisting you by looking at the chat? And then secondly, if you have an assistant who can move the camera so that it covers the large screen as well as the small screen, then you won't be disappearing out to the left of the picture.
Okay.
If you haven't got someone to do that, don't worry. But if you have,
it's in hand.
move it to the left. Thank you.
I don't have access to the Teams link.
Sorry?
I don't have access to the Teams link. So if you want to send me an invite, let's hope I don't fall because this won't be fun. Oh, it doesn't rotate. Good. I guess you will have to.
So, okay, in which case I shall not move. I shall stay put.
Please. I couldn't open this. No one's seen this. I'm not sure.
That's it.
Can you look and see?
Chris, is that better?
Not really, no. But I think so long as we've got the slides in front of us, so we can follow through perfectly well. I think if you don't walk too far across and that's better.
I shall try to stay put.
Yeah, that's fine. No, it's now positioned, covering both the large and the small screen, so you can walk about to your heart's content. Thank you.
Okay, thank you, Chris.
Let me invite myself really quick.
Yeah, hopefully. Okay, so we soon have Payam manning the chat window. Okay, so when we have designed the aircraft, we really like to know how well it flies. So what we need to do is we need to ascertain the longitudinal and lateral handling qualities. Now, to do that, we need to establish the extent of stability the aircraft possesses. We can look at Cooper-Halper scale of assessment, as well as looking at cross-plotting the frequency and damping ratios of the various modes of motion to establish whether or not the aircraft has the correct handling qualities. Now, of course, if you look at CS23 or CS25, it will tell you, or even CSVLA, which is for the very light aircraft, it will tell you what kind of assessments are needed and what class of aircraft this is and what would constitute to be adequate handling behavior of such entities. So the things that we are interested in is, from a longitudinal point of view, is principally the short period pitching oscillation, which for people who are new to aircraft design is a short brisk motion of the aircraft nose when the aircraft is excited with an elevator input. We like that to be well behaved and well damped, with not too high a frequency. If the short period has a high frequency associated with it, then it is likely to impact on the structural side in terms of fatigue. So we like to keep that moderately low. Similarly, we look at the short period damping, as I've already said. We look at control force gradients, how easy is it, or how much effort is needed to move the control surface, etc. We look at cuboid stability, which is basically a long-term motion of the aircraft where it exchanges its kinetic energy to potential energy and vice versa. So, for example, it goes up, then starts to increase in speed. As it increases in speed, it gains more lift, it then climbs up. So it has an oscillating behavior, which is long-term. Now, it can be quite troublesome. Most aircraft will exhibit that motion, some little exaggerated, others not, as the case may be. Similarly, we like to investigate how the aircraft behaves in its lateral axis. And for that, we would need an assessment of the Dutch roll mode, which is a combination motion that involves the rolling and drawing behavior of the aircraft. Directional stability is quite important as well, so we need to do that. We need to look at the time constants associated with the rolling motion of the aircraft, which is essentially the ability of the aircraft to right itself and how quickly it does that. So when the aircraft is disturbed in roll, then how quickly it rights itself would be the time constant. And the time constant we define as the motion, when the motion gets up to 63% of its final steady state value, that's the time that we are interested in. So most motions, one time constant is enough. Some motions will stabilize after maybe two time constants or thereabouts. We also need to know what the maximum stick forces are, especially if you're designing a twin engine aircraft. Then the pedal forces for the asymmetric engine failure scenario then becomes quite important. Why do the tests? Well, as the slide says, we need to do these tests to be compliant. We can do these tests for production flying to prove the capability of the aircraft as intended. We also will do variation testing. So, for example, if you wanted to extend the fuselage a little bit, or you wanted to add a high-lift device, then we can do the extension testing again using software environment. We can also do flight testing from a pragmatic point of view to identify problems. But the main issue with flight testing is it's very, very time-consuming, it's very expensive, and it requires a lot of resources. So how can we evaluate our aircraft designs at the early stage without having to resort to a prototype, without investing a lot of money in hardware? So we currently have a suite of flight simulation packages available, Flight Gear, X-Plane, and Microsoft X. Each software package comes with its, let's say, benefits, at the same time, some negatives or pitfalls. For example, Microsoft X provides a wonderful graphic rendition of the scenery and the aircraft, and also uses mathematical equations, linearized or nonlinear, so in fact I think nonlinear equations to do the flight dynamics. But the biggest issue is it's not easily possible for us to create our own design. So from an engineering point of view, it may not be particularly suited. Flight Gear was a mainstay up until X-Plane came in on its own. So Flight Gear is very similar to X-Plane in terms of how it computes the flight dynamics. Basically, it's the vortex funnel method for computing the forces around the aerostructures. Okay, so we will have a quick look at what explain will do and its directory structure. That's quite important. So when you invoke or when you install explain, and by the way, explain is available from Laminar research site, explain.org, and it is downloadable free of cost. The only issue is that you can only run each session in a time-limited manner. Otherwise, there are no restrictions whatsoever. But the actual package is not that expensive either anyway to buy. So once you have downloaded explain, what you will see is a familiar directory structure where the explain installs itself in a folder in the root directory of your computer called explain, and within the explain what you will have is various directories. Now, as the session progresses and as the let's say the teaching progresses to second, third weeks, we will be mainly modifying those two directories. The aircraft directory, where the aircraft definition in terms of the geometry is kept in a file called .acf, the aircraft file, which is what we're going to design, and the aerodynamic behavior, which will be the pitching moment relationship, the drag relationship, and the lift relationship, or the coefficients in any way, would be held in the airfoil directory called AFL. So all the files are going to be named with the extension .afl. Then you have other host of directories which embody the objects that you may want to use, the liveries, the scenery, and anything else to make your simulation a little bit more realistic. There are three application packages in the explain folder. You will notice one of them is called explain, which is the simulation environment. Then the second one is plane maker, that allows us to define the aircraft geometry and define the mass balance and the propulsion system and control surfaces, etc. So all of that is done through the auspices of plane maker. And finally, we have airfoil maker, where we can then define our airfoil. There is a reasonable amount of airfoil database that comes with explain. So for example, something like a 2412 NACA series, Clark Y, a few Sealing airfoils are already part of explain. If they're not, then we can create arbitrarily the pitching moment, the drag, and the lift characteristics of any airfoil. So to do that, we make use of the software tool called Airfoil Maker. So we will have a session directed directly and involving both the plane maker and the airfoil maker. Now, hopefully today we'll be able to log on to explain, select an aircraft of your choice, and conduct some tests to see how well they perform. So the first test we are going to perform is in the longitudinal motion, where we will trim the aircraft. Now, trimming the aircraft might not be as straightforward as it might appear. By trimming, we mean the aircraft must be flying straight and level, both in terms of direction and in terms of no variation in height or speed. So constant speed, constant altitude, constant angle of attack. Now that's difficult. So if you're not familiar with joysticks and the explain environment, it might find a little nervy. And the reason for that is very simple. In the real aircraft, the control column, especially light aircraft, is connected directly to the control surface. So when I move the control column or the stick or the joystick, then I can not only feel the dynamic pressure relayed through the control runs, wires, etc., but the aircraft responds pretty much instantaneously. Whereas in a flight simulation environment, you have the input of the joystick, which is being read by the computer. It then processes that input, then evaluates the effect of flight dynamics, and then displays it. So there's a lag. So my advice to you is, when you're flying X-plane, when you make an adjustment, can you just let the aircraft respond before making another adjustment because you think the aircraft's not moved? Okay, so you anticipate that computational lag before you apply in. Otherwise, what happens is you apply an input and you don't see the aircraft respond as much as you think it ought to. You apply even more input. But by the time the aircraft has responded, it's moved too much. But then you apply an opposite correction to bring it back. So then, in the end, you're all the time playing with the joystick. So let the motion develop before applying more inputs. Okay? So we will look at the short period pitching oscillation. We will look at phugoid. So for phugoid, what we'll do is we'll get the aircraft trimmed, and we will just do a very gentle tug on the elevator. Just pull it back and then let go of the stick. Then the aircraft should develop that long-term oscillation, what we call the phugoid, which is basically a change in airspeed and altitude. So we'll talk about how we collect the data, how we analyze the data as well. So very quickly, we can look at Dutch roll. Now, Dutch roll is basically a combination motion between rolling and yawing. So to apply the excitation, we will use the yaw and aileron, but opposite. So left rudder, right aileron, right rudder, left aileron, and we cycle it. And once we cycle it, the aircraft will be excited, and then we can see the Dutch roll motion. By plotting the yaw angle versus the roll angle, we can see whether the aircraft is heavy in yaw, which is the wing translating backwards and forward, whether it is predominant in roll, with the wing going up and down, or whether it has an equal amount of yawing and rolling motion, where the wing will be seen to be executing a circular motion during the Dutch roll. Again, we can look at spiral. I'm not going to take too much of your time because we are approaching more or less the end of my spiel, so that we can give everybody a 10-minute breather before we embark on the explain. So again, we will look at spiral mode. Look at the roll subsidence or the roll subsidence, depending on how you pronounce it. Fairly simple one to execute, as long as you've got the aircraft straight and level. The wings must be level. Now, to access data is interesting. So what we need to do is we need access to something that allows us to plot information. Excel is a good starting point. So in Excel, we will open up a tab delimited file produced by X-plane. So whenever we do the flying, X-plane has the ability to save this information to a file, which is then saved in the directory structure as I indicated before. And using that file, which is basically a vertical separated file, I think that is the key just above the shift key and the control to the right of the control key. And that allows us to read columns of data from X-plane directly into Excel, and then we can do all sorts of analysis. For people who are new to flight testing, once we have produced the plots, or let's say the traces, depending on what we need for a short period, we need to have time and the pitching motion of the aircraft, so either pitch rate or pitch angle. For Dutch roll, it's time, yaw and roll. For spiral, it's roll. For phugoid, it's speed and height, etc. So we need to be able to capture those motion variables. Once that is done and we have a plot, the plots could be either damped, so the oscillation will decay, or the plots will indicate very little damping, where the oscillation carries on in time. So this is equivalent to what we term as the simple harmonic motion. So there is no damping. And then, of course, we can have an unstable response where the amplitude of oscillation in any mode, whether it is the phugoid, whether it's the lateral, whether it is the SPPO, the amplitude amplifies in time, so that indicates instability. To establish the principal variables, such as the damping ratio and frequency, we resort to a method known as the method of logarithmic decrement, where we look at the decay parameter based on either successive or separated by so many oscillations. And once we have the decay parameter, then we can use that to establish the damping ratio and frequency in any mode of motion. And that allows us to get the insight into the handling behavior or the handling characteristics of the aircraft. Okay, so for reference, there are many design books. Ajoy Kumar Kundu, that's a nice one. Aircraft Performance and Design by Anderson, that's also a very nice one. You also have Egbert Tornbeek, which is a classical aircraft design book. So we are going to make these slides available to all the delegates after the session. So there's no need for you to make any notes. And finally, we have another design book, which I particularly like, is by Daniel Raymer. It's one of the more, let me say, well-used design books. And of very recent, Snorri Gudmundsson, his book is also very, very good. So if you like the analytical spice, in terms of aircraft design and performance, then Gudmundsson is a very good book. Tornbeek is also quite analytical and mathematical as well, by the way. If you're looking at Mohammad Sadre's design book, that's also very good. It has many of the key features of the other authors, but he also has lots of empirical techniques for independent design of empennage, undercarriage, etc., etc. So if you're looking at empirically designing your aircraft, then Mohammad Sadre's book is actually quite good as well. Okay, I think I have said enough for now. So we'll give everyone a 10-minute break, and after that, we will dive straight. Yes, in terms of the dynamic motion, the inertias, especially the IXX, IYY, and IZZ, are important, because when we look at the lateral motion, there is a concept called the concept of stability derivatives, and these derivatives are effectively formulated with either, in the longitudinal case, the IYY, in the lateral case, the IXX, and the mass as well. So you need to get the mass balance correct and the inertia values correct in order to get a good feel for the dynamic behavior of the aircraft. X-Plane does a decent job, but then again, it is a software environment. It has its limitations, but as a first, let's say, first cut exercise, it gives us a fairly good result. Now, to give you an idea, I've done a lot of work on the Cessna 172 as a pilot myself, as well as a user of X-Plane. The takeoff distance for a 172P in analytical form is around 320 meters. X-Plane comes along and says you can take off in about 310 meters. Okay? And the pilot handbook says you can take off in 308 meters. So they are within 10 to 15 meters. So it is actually quite good. So But it then also depends on how well you formulate your design in the plane maker as well. Okay, so there are reservations, but as a first cut, it's actually quite decent. Right. Another question is, in this software, can we design aerobatic light, EV? And yes, of course we can, because you will then define the propulsion system characteristics in terms of your discharge rates and your battery capacities, etc., etc. And of course, the choice of propellers will enable you to create an EV aircraft fairly easily. Not an issue at all. In fact, I mean, we, as I said, design between 8 to 10 UAVs every year, and they're all electric. So that characteristic is easily one of the parameters within the graphics element to allow X-Plane to run in a windowed mode. So when it runs in a windowed mode, you will be able to have the Teams window open as well as the X-Plane window open as well. For the delegates who are here in Coventry, that isn't a problem. They can carry on working with X-Plane in the full window mode, whereas the delegates who are logged in on Teams will need to make that adjustment. So the minute you have made that adjustment, then you will see X-Plane revert to the Windows mode. So I'm now going to invoke X-Plane by opening up the directory and double-clicking X-Plane. I have already got my installation on my PC to work in a windowed mode. So I can see both my Teams window and all the X-Plane window as well. X-Plane will offer you a startup screen which looks as displayed. Resume last flight, new flight, load save flight, flight school, and settings. So the first thing we're going to do is go into settings. Once the settings window is open, you will see lots of tabs. Those tabs are general, sound, and graphics. So when you get into the graphics screen, so click on the graphics tab, there are many features available that can affect the performance of X-Plane. And that includes the visual effects, the anti-aliasing, the texture quality of the graphics that the system generates, etc. Also, to get more and more realism, you might find playing around with the number of world objects. So you can drag the slider, so X-Plane automatically generates traffic, bridges, trees, buildings, etc. So the outside world objects, the more you have, the more graphic intensive the whole operation becomes. Whereas if you're only interested in flight evaluation and speed is of the essence, then you would keep the outside world objects to a minimum. So what we need to do is to come down to monitor configuration. So monitor configuration is halfway down the screen, and click on monitor usage. And in the monitor usage, you will see multiple options. And one of the options is windowed simulator, which means that it will work in its own independent window, not taking up the entire screen. So for the delegates who are online, can they please go to the windowed mode? For the delegates who are present in Coventry, they don't need to make that change. And when you're done with making that change, we click done, and that allows me to run X-Plane in the windowed mode. The menus are self-explanatory. However, there is just one or two things that I'd like to mention at this stage. When we are doing flight simulation, it is quite possible that you may have conducted some tests and you may have saved some data. And you may want to resume your experiment from where you left. So it is possible for the X-plane environment to recreate your previous mission and put you exactly where you left. So resumption of last flight is actually quite interesting, because it may not be possible for you to conduct the entire flight testing regime during one flight. So what you do is you can leave it and then resume the old flight to take up the testing from where you left. So that's an interesting one, but that then requires you having completed a flight, which means a flight must exist for you to invoke that mode. The second menu is the new flight, and that is what we will use today. Invoking new flight allows us to choose the aircraft, choose the environment, i.e. an airport, and also choose various other parameters of interest, such as the weight balance, CT position, etc. So we will make use of the new flight function to start the simulation running. Any flight can be saved and can be retrieved using the save flight option. And finally, for people who are interested in learning how to fly, X-plane has what we call a flight school. So clicking on the flight school takes you up into an area where elements of flying can be learned. So for example, X-plane basics. So there's an online tutorial in terms of X-plane basics. If you want to take off, if you want to land, or if you want to experience and practice some traffic patterns around an airfield in a simulated environment with other aircraft being generated by the AI. What X-plane also allows you to do is we can network all the PCs and have a multiplayer scenario, which means that all of us present either virtually or in real can be logged on to the same network, and we can all be flying our airplanes in the same environment, okay? So we can then play dodgems quite nicely. Okay, so the flight school is an option. If you want to learn to fly, then do look at that option, and that will give you good pointers towards how effectively to use X-plane. So we'll close that window by returning to the main menu, and this time we're going to invoke new flight. When we invoke the new flight option, Laminar Research have created a fair amount of aeroplanes by default. For example, you might have some military aeroplanes, there's a seaplane, there's a helicopter as well, and of course there are some ultralights, and there are some big commercial airliners such as the Boeing 737, the 747. I particularly like the 747 model. It actually is very representative in terms of how one expects it to behave. General aviation aircraft, lots of them. We are going to use the Skyhawk with the conventional six-pack. By six-pack, we mean the conventional analog instruments. If you are interested, there is a version of Skyhawk available on X-plane, which is what we call the G1000. So there is a multifunction display, two of them or three of them, I don't know how many there are, but it's the Darwin 1000 interface. So if you are interested in that environment, that's also available. But we will look at the Cessna Skyhawk. So we click that, and then from a simulation point of view, we have an airfield to choose. So there's a whole array of airfields that X-plane comes with. If you are interested, X-plane also has what we call photorealistic scenery available as well, but that is an add-on. The default scenery is not bad, but if you are really interested in realistic flight simulation, then I suggest that you look at acquiring the high-resolution photographic scenery, which is available for bulk of Americas, some European countries, and also Australia and New Zealand as well. In terms of the default data, the default data is something like the sort of 50-meter SDRM data, whereas the photorealistic scenery is going to be coming down to something like 6 to 8 SDRM data. So we can choose the weather, we can choose the time of the day. So by choosing the weather, we can go to foggy conditions, to completely clear conditions with different types of cloud formations in the scenery. So by changing that, we are able to simulate the environmental conditions. Now, X-Plane also has a very advanced feature. If you link X-Plane to the Met Office site, then it can actually get the weather information and try to recreate the weather that may be present right now in Coventry or wherever you are in the world. Okay, so that is also quite a nice feature of X-Plane. But we are going to choose a clear day. It's easy to see everything and it's easy to fly. And we are going to use around midday so that the visibility is good. And once we're happy, then we need to select an airfield. We can choose any airfield. If the scenery exists, it will display nice objects. And if the scenery doesn't exist, it will revert automatically to either a grass strip or a strip with water around you. So there's a default configuration, but all you need to do is, if you install X-Plane, install the scenery as you're installing it based on where you want to fly, and then you will have good resolution scenery with good objects in the areas you're going to fly. If you install the entire package, it comes over 6 DVDs and it's gigabytes of installation. Whereas whilst installing X-Plane, if you choose a segment of the scenery, right, which it gives you the choice whether you install the entire world scenery or localized scenery, we can then narrow it down and just have a fairly slim version of the installation. I'm just going to change to Coventry. Coventry is EGBE, because I know there are some buildings that will come up by default and the airfield looks familiar. So we'll use EGBE for Coventry, but the online participants, if they wish to use a local airfield for where they are quite happy to do so. So we then go to start flight. Now this is where the patience is tested. Depending on what you have configured the system as in terms of its graphic rendition or graphic render, if you've chosen lots of outside world objects with anti-aliasing, blah, 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 then it's going to take a long time for it to boot up, okay? So just be patient, and when it does install, you will see an aircraft at the threshold of the runway of your chosen airfield. Now, a quick note at this point in time, particularly for the people who are online, is that X-Plane is available for free, and if you don't have the bought version, which will have what we call the DVD number 1 that you install in your CD drive, that removes the time limitation. You will be limited to 10-12 minutes per session, and that I find is adequate to do a lot of work. So don't be dissuaded or don't be frightened that you don't have the full bought-in version. Even the trial version allows us to do a lot of work. Okay? So as I said, it is a test of patience. So whilst the aircraft is being loaded, we just have to either bite our nails, drink coffee, or make idle chat. Assuming it doesn't crash. So my machine is all up and running, and I have a typical six-pack arrangement on the screen. Thank you.
One technical question, if I may.
Right?
One technical question, if I may.
Sure.
Is there, with Explain, is there a patent implication involved for anything designed on Explain? Should someone take that design and decide to commercialize it?
Entirely up to you, because it is a public software in public domain. It comes with the normal caveat that it is in public domain, it is free, gratis, you can use it to your heart's content.
Just in your house, not for commercial purposes.
Sorry?
Just in your house. Not for
Yes,
there
but
is
I mean, if you
commercial
want to then use it for commercial purposes, there's a commercial license available as well. You can design an aeroplane, you can't go and sell it.
Fair enough. Well, that's what I was asking. Yeah.
For that, you need the commercial license.
Fair enough.
And that's available. Okay, so I'm assuming that everybody's computers are up and running. Now, what you will see is there is no menu system. However, if you hover your mouse on the top of the window, you will see a menu system. That menu system allows us to configure Explain and also allows us to perform the tests, etc. So for example, I'm going to very quickly go through that menu system and identify some of the interesting menu items which may be of help to us. So the file menu is a typical Windows file menu, nothing extraordinary there, apart from the fact that it is able to open a checklist. So if you're flying for fun, and if you're flying a Cessna and you wanted an online checklist, which is also what we call the electronic flight bag, so by clicking on that, you can bring up a checklist so you can go through the procedural elements of the flying as well. The next menu, which is interesting, is the flight menu. And this is where a lot of configuration is going to take place. So for example, we've already been to the flight configuration, which is by selecting the aircraft and selecting the airport and selecting the weather, etc. Then what then remains is editing the weight and balance. So by clicking the weight and balance, you're able to alter the location of the CG, what payload you carry, etc. So the amount of fuel you're carrying, etc. So you can actually set all those parameters in that environment. Once you've done it, clicking done takes you back to the main menu. If you go back to the flight configuration, we can resume flight and you're back to the main screen. So you can go from one mode to the other quite effortlessly. The other interesting menu items would be when we are trying to fly straight and level, it might not be that easy, but I believe we have Mike Jump online from Liverpool University. Mike, would you be so kind to share the videos of how to use the Garmin 1000 for providing some of the flight and level work for getting the data. So would you like to share the link, the YouTube link for the videos that you have been making?
Will do. Yeah, I can hear you. Can hear me. So yeah, I'll just post them in the chat.
So for our reference for the delegates, Mike's again an associate professor in Liverpool University. And he also has been flying for best part of his life. He flies light aircraft, and he is involved quite heavily in flight simulation work as well. So thank you very much, Mike, for that. Okay, so that's basically as much as I'd like to see, but there are other options as well. For example, you can manage the keyboard and joystick from this menu. So when you want to map a new joystick, in terms of being able to map the throttles, the ailerons, the elevators, the rudders, etc., then you are able to do so by clicking that option. When we come to the view menu, the view menu allows Explain to display or exhibit different views of the aircraft from different perspectives. So for example, we can have a view from inside the cockpit, or we can have the view from a chase plane, or we can have the view from whichever angle you wish. Sometimes that's necessary as well from a testing point of view. Then there are some other effects. So for example, you can have the in the cinema mode, you can introduce camera shakes, etc. In the sunglasses mode, the view will appear as if you're wearing sunglasses. If you go to the night vision goggles, so the view of Explain will become as if you are wearing the night vision goggles as well. So different ways of looking at the information is also presented. If you go to the view, change internal view, you can either have a default view, you can have a 2D panel, 3D panel, etc. So do play around with those menu options to see what those menus do. Okay, the next important area of the screen is the developer area. Now, this comes in quite handy when you are either developing a plugin for Explain. Now, let me just say something at this point. Explain allows users to develop a plugin. A plugin is a standalone executable code that Explain will execute for you. So for example, a long time ago, I was responsible for developing an interface between synthetic instruments and Explain, and where we developed this plugin to interface external instruments to Explain. And these instruments were basically done through stepper motors and what have you. Okay, so it is possible. So what then happens is Explain has a concept of data references or properties, and these data references and properties are made available through the interface which allows developers to develop their plugins. So these plugins can do anything you wish. For example, if you wanted to work on hardware in the loop simulations, then the plugin will allow data in UDP format for people who are interested in networking, the unified datagram. You send that data to your hardware, which interprets it, manipulates it, and then sends the commands back to Explain. So then Explain then becomes a very nice environment to visualize your flight. So all sorts of things are possible with Explain. Hardware in the loop simulations are possible. And so are software in the loop simulations are possible. People who are interested in developing their own control algorithms can make use of Simulink and MATLAB interface with Explain to develop all sorts of exotic controllers for use in their design. So there's a lot of possibilities here. So the developer section and the plugin section allows us to do that. On the right hand of the screen, you will see some quick access buttons, which will access various elements. For example, I can pause the simulation anytime. I can also use a keyboard shortcut. For example, the character P pauses, and toggling it restarts the simulation as well. But the most interesting one that we need to look at is but by the way, that little icon there, which is like a little balloon with a circle, that allows us to display the instructor station for us to introduce faults and errors when somebody is flying. This menu item is of particular interest. So when we click it, it goes back to the settings menu. And in the settings menu, what we are interested from flight testing point of view is the data output tab. So clicking on the data output tab will bring about a whole raft of data references or variables. Now, the interesting thing here to note is there are 4 columns. The first column is show in cockpit. The second column is data graph window. So that basically allows you to produce a graphical output of the variable of interest on the screen. And the third column, which is what we're going to use for the analysis purposes, is the disk data output. Now that is the interesting bit. Now, if you want to do hardware in the loop simulation or software in the loop simulation, then the fourth column allows data to be transferred over the network to any computer that is capable of receiving the UDP datagram. So, in majority of the flight testing, we would like to use obviously a reference, and that reference is time. So we will look at and click the times. So once I check the times, then all sorts of timing information will appear in my data file. Now, whilst we are doing the testing, it is sometimes a good idea to display some information on the screen as well. So we will output the same information on the cockpit as well, which is basically the same as on the screen. Other things that we need, as I have already said, we will need information on the pitch angle, the roll angle, the yaw angle, the pitch rate, yaw rate, roll rate, various accelerations, the normal acceleration, the lateral acceleration, the longitudinal acceleration. All of those are available as variables of interest. So for example, if you go to row number 17 and row number 16 are the angular accelerations, and also you will find the pitch, roll, and yaw information. So we click those values as well. If you want to find a variable within the data reference, you can point your mouse to the search, click on the search button or search area and type, for example, I typed in COEF or COE, and it says what's available there is lift over drag and coefficients. Now, particularly useful because I'm going to get the aerodynamic efficiency, lift to drag ratio. I'm going to get the lift coefficient CL of the entire aircraft, and also the drag coefficient of the entire aircraft as you're flying through the test. So we can show in cockpit, and we can show on the disk data file. Okay, so that is how much I want to say at this stage. And what you will then see is, after having selected those variables, you will see a display in the left-hand corner of your screen, which will indicate what is the variable that you've outputted and its current value. Now, I chose the lift to drag ratio, the CL value, and the CD value. And I'm also looking at the propulsive efficiency as well as E to P. So that's all there is to it. Now what we need to do is we need to fly the aircraft. To fly the aircraft is very simple. You will advance the throttles on your joystick and hit the brakes off. So the letter B on the keyboard allows us to advance the aircraft. So brakes off, and then we just fly. So the first exercise is being able to take off. Just a quick reminder, the Cessna will rotate around 50-55 knots. So let the aircraft speed build up to around 50-55 knots, and then a gentle pushback on the yoke will allow the aircraft to fly. So your first task for the day is to fly straight and level. Get up to about 2,000 feet and see if you can actually fly the aircraft straight and level.
The aircraft is tumbling for itself.
Sorry?
The aircraft is tumbling for itself.
Well, I'm not in control, therefore the aircraft is doing all sorts of funny things.
I feel sorry for that pilot.
Because I'm not flying it.
I already managed to cycle the view by pressing that. Cycle back.
Okay, so in that case, what you do is you go back to the mouse.
I think the altitude there is showing in meters. That doesn't.
Okay, so throttle, and then
I absolutely am.
You've seen it on I don't know. You go to GTA or
Oh yeah,
default speed.
I just
Look at the RPM
Make sure
gauge,
you recheck
see
the
if the RPM is increasing when you throttle. That's in forward.
I was looking for it actually.
You can.
There you go.
Yeah, I know. I think
So now you need
chasing
to
you, and I was like, okay.
enjoy it,
That's one of those things that doesn't stop me from trying.
let the speed build up.
Please break stop.
So it's around 55 knots.
That should be okay.
Maybe
This will change how you. I would really recommend you look at the control layout. Yeah.
Okay, so what you do, ratio any trim controls and advance the throttles
Show key shortcuts.
and manage the rudder,
Show key shortcuts.
keep the aircraft in center line,
We go back to that menu.
wait for the speed to build up. So speed
Manage.
is 55 knots. So that I think is about 55 knots.
Nico, where was the joystick?
If you go to settings, you should have there should be a joystick tab there. Yeah.
The menu you showed in the class, was it this thing, the dashboard?
Yeah, but you were all over the place. You should not.
It's in the book.
Should we go through like the basic joystick control?
They are standard PCs. The simulator stations are on the ground floor. We have rather sophisticated flight simulators in the ground floor, 5 of them. They have a motion seat with a dome display, with a MFD, a 3-tube MFD. So fairly sophisticated simulators downstairs. Maybe in the second session, I can quickly show you the simulator setup that we have. We also have a very large simulator representing an Airbus 320 as well. But that's predominantly used for research purposes.
go down and turn my video on. Right? Go down and turn my video. You don't post a picture.
Tree controls. Pitch tree. Those keys, that is to pitch down.
Now, interestingly, whatever variables that you had outputted will be transferred to the data file. If I may very quickly go back to the data refs. So go back to the settings and go back to the data. What you then see is the disk rate. So on the right hand side, you will see the graphical rate, how many packets per second. We can have the UDP rate, how many packets you want to send over the network, and also how many samples you want to write per second. So at the moment, it's going to write 10 at 10 hertz, 10 samples a second. So everything that you have outputted will be written 10 times a second. That's a lot of data. So if you were to fly for 10, 15 minutes, you can well imagine how big the data file is going to be. Okay, so depending on the test you want to perform, set your data rate appropriately. For example, when you want to look at the roll mode or the short period pitching oscillation, you want to look at something like 10 hertz. Whereas if you're looking at the long-term mode, such as the phugoid, then having a 2 sample per second is adequate, because that's a mode that's going to persist in time for well over 60 seconds or more. Okay, so that'll be enough data for you to be able to chart properly. So 10 hertz is adequate for my purposes for now, so we're going to leave this untouched. So who's found flying straight and level straight and forward? Who's be able to fly straight and level? Yeah, everyone? Straight and level? Okay, so once you've got the aircraft flying straight and level, I want you to sharply pull back the stick and let go and see how the aircraft responds. And let go of the stick. So a sharp input into elevator and then see the aircraft performance. So it exhibits a heavily damped short period oscillation. Damping ratio in excess of 0.7. And the frequency is around 0.8 to 1 radian per second, which we'll be able to extract from the data file once we get into it. Happy?
Yes.
Okay. So everyone's had a chance at flying the aircraft and trying to fly straight and level, and everyone's been outputting some information onto the disk as well as the screen. So what we now need to do is look at this dreaded data file. Okay. So what we then need to do is we need to close explain. So go to File menu and say Quit, and that terminates that session. Yep. So once the session is terminated, all the data is going to be stored in the file called data. That file there. It's a text document formatted with the vertical separator, which we now need to open up using Excel. So to do that, I go to my Windows menu. If you have a copy of Excel, then invoke Microsoft Excel. When Excel opens, you want the blank workbook. A blank workbook opens. Then using the file menu, I want to open a file from this PC, or I can do a browse. If I do a browse, then I can look at my root directory, and in the root directory I will have explain, and in the explain directory I want all files, and that will include the data file as well. So I need to click on that. And if I open it, then Excel gives me an option to read that data file in columns. So what I want to do is I want to select delimited. So it is a delimited file. And the delimiter used by moving to the next screen is a other, and in other I want shift vertical separator next to the shift key. So the vertical separator is next to the shift key on the right hand side, just above the control key and the Windows key. The minute you do that, all the data appears in columns. And by selecting finish, Excel produces nicely ordered columns of data. The first or the second row will include a tag indicating what that column represents. For example, the real time, the mission time, the Zulu time, the local time, the times on the hobs, the indicated airspeed in various axes, and of course, right at the end, I also outputted the pitch rate, pitch angle, roll angle, heading, etc. So all of that information is available. But now you're going to ask me, I also at some stage wanted lift and drag coefficients. Where have they disappeared? So what happens is every time you add more variables, the file will grow. So if you scroll down to the bottom of the file, wherever I've made changes to the output, you will see a new header. There's a lot of data there. There. So that's where I changed my variables, and again, those bits of information will appear in the data file. So to plot anything is actually quite simple. You just need to select the two columns and ask Excel to plot the data. So I'm just going to do a random thing. I'll just take two columns by random and insert using Excel a data plot, a scatter plot, or a bubble plot, or anything you want. So data then appears. It's as simple as. Okay. Now, what's the clever bit? The clever bit is knowing when you started a particular test. Okay. So what I suggest we do is we output the mission time on the screen. So by using the pause function, So we pause the simulation, note down the mission time, unpause it, conduct your test. As soon as the test is finished, pause it again. Note the mission time again. So when you go through the data file, you'll be able to go to the start of the mission time, end of the mission time for a particular test. And then you'll be able to access just that specific rows of data rather than the whole data file. So it's always a good idea in Explain to use the mission time and use the pause feature to start and stop your tests. Okay, it's almost the end of the session, and I very much hope that we have taken something away in terms of learning points. I may have instilled some confidence in you for you to be able to use Explain as a serious tool for evaluating the characteristics of airplanes. Now, in the second session, we are going to be looking at the mechanisms whereby we create new aircraft designs. So we will be looking in depth at a plane maker as well as airfoil maker as well. So using those two, we'll be able to either create our own new aircraft or use an existing aircraft and alter it. Okay? Now, for that, we may have to do a little bit of what I call jiggery-pokery, because the C drive on university computers is not writable, so it is read-only. So what we'll do is we will copy the aircraft onto a USB stick, and then using that USB stick, we'll be able to modify the existing aircraft. Okay, so it's not a big deal. It's something that is very much possible. I'm going to hand you back over to Chris. Chris, would you like to conclude the session for me, please?
Okay, can you hear me?
Yes, indeed we can.
Well, thank you very much, Rashid, for all you've taken us through today. There may be some who, like me, are lagging behind a bit. I'm afraid my X-Plane didn't load properly. I couldn't get I could get as far as getting the window screen, but I couldn't get any further than that. It wouldn't load my wouldn't load the Skyhawk and so on. So I was following you through, and I'll have to do some work between now and next time to actually practice some of the things which you've shown us.
Okay.
And
Chris, let us interject. What I might be able to do is the team session will be alive, as it were. It will stay. And I'll upload some YouTube links in how to use Explain. So people who were lagging behind will be able to watch YouTube videos on how Explain needs to be configured and used. If that's okay, then I'm quite happy to do so.
Thanks very much. I'm sure many of us will find that useful. And so thanks very much for today. And you've taken us through at quite a pace and covered a huge amount of ground. I hope everyone's found it useful. We will in time have a feedback system for you to actually make comments. And we'll be able to say more about that next time, probably. So,
right,
Barry, do you want to?
Thank you, everyone, and thank you for listening to me and being patient and asking some really good questions as well on the track. Thank you.
Thank you very much.